The year 1674 marked a pivotal moment in the trajectory of mathematics, witnessing the unveiling of Isaac Newton's On the Analysis of Equations with an Infinite Number of Terms. This treatise, though existing in manuscript form at the time and shared among a select circle, laid the groundwork for a revolution in mathematical thought. To appreciate its significance, we must first understand the intellectual climate that nurtured its genesis. Prior to Newton's work, mathematicians grappled with the limitations of existing algebraic techniques. The burgeoning field of calculus, while showing tremendous promise, was still in its infancy, reliant on cumbersome methods and lacking a fully formalized structure. The manipulation of infinite series, a crucial component of Newton's approach, was understood only intuitively and tentatively explored by predecessors like John Wallis and James Gregory. Wallis' work on areas under curves and Gregory's series for the arctangent function hinted at the potential of infinite processes, yet lacked the systematic framework needed for general application. Newton, therefore, inherited a landscape ripe with potential, yet burdened by the constraints of existing methodologies. He sought a unifying principle that would allow mathematicians to tackle a wider range of problems, specifically the solution and manipulation of algebraic equations. The central innovation of On the Analysis lies in its systematic application of infinite series to solve equations, a technique that extended the reach of algebra far beyond the limitations of finite expressions. Newton recognized that a function could often be expressed as an infinite series, much like a polynomial with an infinite number of terms. This offered an elegant way to represent a wide range of functions, including those that previously defied algebraic manipulation. He developed a general method, equivalent to what we today call the binomial theorem, that allowed him to derive expansions of expressions like the square root of, or the cube root of, or any power of a binomial, extending the theorem to accommodate fractional and negative exponents. This was a profound leap forward. Newton's method, at its core, involved a recursive process. Given an equation, he would transform it into a form suitable for series expansion. He would then employ his generalized binomial theorem to find the coefficients of the infinite series, effectively approximating the solution to the equation. This elegant approach allowed the approximation of a solution to any desired degree of accuracy. As a specific example, consider the equation y squared plus xy plus x cubed equals 0. Newton could find the solution for y in terms of x by using series approximation. This method was extremely versatile and capable of solving problems that were previously unsolvable using existing methods. The power of this method was immediately evident in its ability to tackle problems in diverse areas, from finding areas under curves to solving differential equations. The immediate impact of On the Analysis was substantial. Though initially constrained by its limited circulation, it provided a powerful tool for manipulating equations and finding solutions, particularly for problems in the nascent field of calculus. Mathematicians could now calculate areas and volumes with greater ease and precision. The core ideas of On the Analysis allowed Newton to derive a series for the sine function, which, in turn, enabled improvements in astronomical calculations. This was a clear advancement over existing methods. These advancements also facilitated the further development of optics and mechanics, fields that would continue to refine Newton's original work. The long-term influence of On the Analysis is immeasurable. It provided the foundation for the development of modern calculus, alongside the independent work of Gottfried Wilhelm Leibniz. Leibniz, independently, developed a similar method, but Newton's work exerted a profound influence of the systematic approach to infinite series. Newton's notation, although differing from that later adopted by Leibniz, emphasized the power of algorithmic manipulation, a critical influence on the subsequent evolution of calculus. The techniques presented in On the Analysis enabled mathematicians to tackle a wider range of problems in physics, engineering, and other scientific disciplines. Subsequent mathematicians and their work were profoundly influenced by Newton's approach. Brooke Taylor, for example, building upon Newton's methods, developed Taylor's series, a method of representing functions as infinite sums of terms calculated from their derivatives. This generalized Newton's approach, providing a powerful tool for approximating functions and solving differential equations. The development of the theory of functions of a complex variable, a cornerstone of modern mathematics, also owes a significant debt to the ideas presented in On the Analysis. The systematic use of infinite series became an essential tool for understanding the behavior of these functions. The reception of On the Analysis, during Newton's lifetime, was a complex interplay of admiration and controversy. While the mathematical community recognized the power of his techniques, their reliance on infinite series and the lack of a fully rigorous justification for their use raised some eyebrows. The concept of infinitesimals, central to the underlying calculus, was initially viewed with skepticism. Some mathematicians questioned the validity of manipulating infinite quantities in the way that Newton proposed. However, the effectiveness and clarity of his methods were undeniable. The success of his solutions to various problems, particularly in physics and astronomy, eventually overcame the initial reservations. Key contributors significantly influenced the development of the analysis. John Wallis' work on infinite products and areas under curves paved the way for Newton's understanding of infinite processes. James Gregory's work on series expansions also offered critical insights. Newton, in turn, acknowledged these influences, recognizing the value of their contributions. The analysis directly influenced numerous subsequent works. Newton's methodology provided foundational concepts for his subsequent masterpiece, Principia Mathematica. The binomial theorem and the methods of series expansion were crucial tools in his development of the laws of motion and universal gravitation. Many of the techniques were refined and extended during the development of the Principia. The methods in the analysis also found applications in the development of optics, particularly in Newton's work on the composition of light. His analysis of the refraction and dispersion of light drew heavily from his understanding of infinite series and their applications to the study of curves. The influence of the analysis on these later works underscores its fundamental importance to Newton's overall scientific achievement. Furthermore, the analysis helped to inform the work of future mathematicians. In conclusion, the analysis of equations with an infinite number of terms represents a watershed moment in the history of mathematics. It was a systematic approach to the problem of solving equations. Newton's pioneering work provided the foundation for modern calculus, the systematic application of infinite series, and the development of the generalized binomial theorem extended the reach of algebra, opening up new avenues for scientific inquiry. Its influence extended far beyond its initial publication, shaping the development of mathematics and its applications for centuries to come. This work, therefore, serves as a testament to Newton's genius and his profound impact on the trajectory of human knowledge, solidifying his place as one of the most brilliant minds in scientific history.